Florida has seen some of the biggest megaprojects ever built in the United States. From colossal stadiums to extensive transportation networks, these builds pushed engineering and budgets to the limit. Let's explore Florida's biggest megaprojects of all time and the staggering ambition behind each one. In the southeastern corridor of the United States, where infrastructure development often grapples with both dense urbanization and expansive wetlands, the construction of the Brightline high-speed rail line connecting Miami to Orlando represented a major engineering endeavor. This privately funded rail project was designed not only to introduce high-speed rail to Florida, but also to demonstrate the viability of higher-speed passenger rail service within existing and constrained right-of-way corridors. The execution of this project required a comprehensive integration of new track construction, upgrades to existing freight corridors, and the implementation of advanced signaling and safety systems. Initial site work commenced with a detailed geotechnical analysis of the entire corridor, which spanned over 200 miles. This included evaluating soil stability, drainage characteristics, and subsurface conditions, particularly through the swamp-prone regions of Central Florida. In areas where existing tracks were used, such as the Florida East Coast Railway corridor between Miami and Cocoa, crews had to reinforce subgrades, replace worn ballast, and realign curves to support sustained higher speeds. Track geometry was meticulously adjusted using specialized rail alignment equipment to ensure smooth transitions and compliance with Federal Railroad Administration safety criteria. For the new segment between Cocoa and Orlando, a greenfield corridor was constructed largely along the State Road 528 Expressway median. This presented its own suite of engineering challenges, notably the design and construction of elevated track sections and bridges over sensitive wetlands and stormwater retention zones. Precast concrete girder spans were transported and installed using massive mobile cranes to expedite assembly and minimize environmental impact. Track beds along this route were laid on compacted sub-ballast, topped with engineered ballast layers, ensuring long-term durability under the dynamic loads imposed by high-speed rail operations. The track system employed continuously welded rail, which was delivered in long segments to reduce the number of expansion joints and improve ride quality. Rail thermite welding teams were deployed to join these segments on site with strict quality control to ensure alignment and weld strength. Dual track configurations were introduced in several key sections to allow bi-directional travel and service flexibility, especially near the Orlando International Airport terminus. Stations were another significant component of the build. The Miami Central Station, integrated into downtown Miami, required a complex vertical design solution involving multi-level platforms, elevated passenger concourses, and integrated commercial development. Structural steel framing supported concrete deck slabs, and the entire facility was constructed above active roadways and in proximity to other mass transit systems, necessitating rigorous coordination and sequencing of construction activities. Advanced signaling and communication systems were installed throughout the corridor, including positive train control, to ensure operational safety at high speeds. Grade crossings along the route were upgraded with quad gate systems, median separators, and enhanced warning devices to reduce the risk of vehicle-train interactions. Along the newer segments, full grade separation was implemented via underpasses or overpasses. Stretching across the southern portion of Florida, the Everglades represents one of the most unique and delicate ecosystems in North America, and the series of restoration projects aimed at rehabilitating this landscape stand as some of the most ambitious hydrological engineering efforts ever undertaken in the United States. These projects collectively focus on undoing decades of human alteration that disrupted natural water flows, severely impacted wildlife habitats, and degraded water quality. The engineering challenges associated with these efforts are vast, involving large-scale earth-moving, hydrological modeling, structural water control features, and long-term adaptive management. At the heart of the restoration initiative is the re-establishment of natural sheet flow, which refers to the slow, shallow movement of water southward across the Everglades flat terrain. Historically, this flow was interrupted by the construction of levees, canals, and pumping stations that redirected water for urban and agricultural uses. To address this, engineers have designed and constructed massive flow equalization basins, stormwater treatment areas, and pump stations that carefully mimic the timing and volume of historical water deliveries. One of the key undertakings involved the removal or modification of hundreds of miles of canals and levees, such as the partial deconstruction of the Miami Canal and the rerouting of flow into restored wetland corridors. This work required precise excavation and reshaping of land to ensure that water could once again disperse evenly and slowly across the landscape. Earth-moving operations were executed with amphibious excavators and low ground pressure tracked vehicles to reduce soil compaction and environmental disruption. In areas where water storage was a major constraint, large reservoirs were constructed, some exceeding tens of thousands of acre-feet in capacity. These reservoirs are lined and equipped with high-volume inflow and outflow structures controlled by gated spillways and electrically operated valves. Their purpose is to capture stormwater during wet seasons and release it in a controlled manner during dry periods, mimicking natural hydrological cycles. Adjacent to these reservoirs are extensive stormwater treatment areas composed of shallow, vegetated cells that use aquatic plants like cattails and submerged vegetation to remove excess phosphorus and other nutrients. The restoration projects also necessitated the construction of extensive culvert networks and bridges to allow water to pass underneath roadways, particularly along major east-west transportation corridors such as PortMiami Trail. These structures were designed to accommodate large volumes of slow-moving water without impeding traffic or causing structural undermining. The foundations of these bridges were pile-driven deep into stable substrata, and the superstructures were built using pre-stressed concrete beams capable of withstanding Florida's corrosive and humid environment. Monitoring infrastructure is integrated throughout the system, including flow gauges, water quality sensors, and automated telemetry stations. Data collected from these devices feed into centralized control systems that allow engineers and hydrologists to make real-time adjustments to water releases, ensuring ecological targets are met. The adaptive management strategy also includes provisions for ongoing modifications as performance data accumulates over years of operation. Set amid the subtropical lowlands of Central Florida, the construction of the Walt Disney World Resort in Orlando represented a pioneering feat of engineering, site development, and logistics management on an unprecedented scale. Spanning over 40 square miles, the transformation of this expansive and largely undeveloped land into a fully functional entertainment and hospitality complex required not only creative vision, but also advanced technical planning across multiple disciplines, including civil engineering, structural systems, utilities, transportation, and geotechnical stabilization. The first major task undertaken was the extensive site preparation, as much of the land was composed of wetlands, swamplands, and pine flatwoods with limited load-bearing capacity. To make the site suitable for large-scale construction, engineers employed a vast drainage and land reclamation strategy. A series of canals, retention basins, and stormwater management systems were excavated to control the water table and direct excess runoff into purpose-built bodies like Bay Lake and the Seven Seas Lagoon. This required dredging operations, the installation of culverts, and the construction of pump stations to regulate flow in both flood and drought conditions. Foundational work across the resort faced challenges due to the high water table and soft underlying soils. To ensure structural stability, deep foundations such as driven concrete piles and auger cast piles were commonly used, especially beneath heavy buildings like resort hotels and amusement park infrastructure. For lighter structures, engineers used preloading and surcharging techniques to compact the subgrade. In certain areas, soil cement stabilization and geotextile reinforcement were added to increase load distribution and prevent long-term settlement. Perhaps the most iconic aspect of the site's infrastructure was the creation of the so-called utilidor system beneath the Magic Kingdom. Rather than being true underground tunnels, these service corridors were constructed at the original ground level. The rest of the park was then built atop a massive earthen berm created by the spoil from the lagoon dredging. These utilidors house all the park's essential support systems, including electrical cabling, water distribution lines, HVAC systems, waste disposal, and logistics corridors, allowing for seamless and invisible operations above. Utility infrastructure was designed with redundancy and scale in mind. Independent water treatment and wastewater facilities were constructed on-site to handle the large demand. Extensive power distribution networks, including multiple substations, were integrated into the landscape to provide uninterrupted electrical supply across the property. Chilled water systems were installed to provide air conditioning via underground piping loops, using centralized plants that optimize energy efficiency. Transportation planning also played a critical role. A multimodal network was engineered to facilitate the movement of guests and goods, including monorail lines, ferryboat systems, internal bus loops, and service roadways. The monorail system, composed of elevated precast concrete beams supported by reinforced concrete piers, was built with precise tolerances to ensure smooth travel and high passenger throughput. All stations and transfer points were constructed with ADA, compliance and capacity planning in mind, utilizing modular concrete platforms, steel framing, and covered walkways. The scale and complexity of building the Walt Disney World Resort in Orlando set new benchmarks for themed development and remains a masterclass in how multidisciplinary engineering can be applied to create not just buildings or rides, but an entire controlled and immersive built environment engineered to handle millions of visitors each year with both efficiency and spectacle. Rising from the urban fabric of downtown Miami, the Miami Worldcenter represents one of the largest and most complex mixed-use developments in the United States, combining residential towers, retail space, hospitality venues, and transportation infrastructure within a tightly confined and highly active metropolitan zone. From an engineering and construction perspective, this multi-block development introduced significant challenges in staging, subsurface coordination, and structural integration across disparate building types, all while maintaining operational continuity in one of Florida's busiest urban centers. Site preparation began with extensive demolition and clearing operations. Much of the project footprint was previously occupied by low-rise commercial buildings and underutilized parcels, which required systematic dismantling and remediation. Excavation crews were tasked with removing foundations, underground storage tanks, and legacy utilities while coordinating with the city to preserve or relocate critical service lines. Due to the high water table, typical of coastal Miami, dewatering systems were installed early in the process, using deep well points and submersible pumps to manage groundwater during foundation work. The structural design of the various towers and podiums involved a combination of reinforced concrete frames and post-tensioned slabs, tailored to meet both vertical load demands and lateral wind forces characteristic of hurricane-prone South Florida. High-rise residential components, some exceeding 50 stories, were supported by deep pile foundations driven into stable limestone strata. These piles were tested using static and dynamic load tests to confirm bearing capacity and settlement behavior prior to full-scale construction. To accommodate multiple uses within tight spatial constraints, engineers designed large podium structures that span entire blocks and house parking decks, retail space, mechanical rooms, and loading docks. These podiums utilized cast-in-place concrete cores and transfer slabs, with integrated fireproofing and acoustic treatments to separate commercial activities from the residential levels above. The coordination of vertical transportation systems, including high-capacity elevators, escalators, and stairwells, was managed using 3D building information modeling to avoid clashes and optimize flow. One of the most technically demanding aspects of the Miami Worldcenter was its subterranean utility coordination. Given the density of existing municipal lines and the proximity to the Metrorail and Brightline stations, all underground installations, ranging from electrical conduits to stormwater management systems, had to be precisely routed and sequenced. Redundant systems were designed for critical infrastructure, including dual water feeds and backup generators located above flood elevation in compliance with updated coastal resiliency codes. Facade systems for the towers included unitized curtain wall assemblies with insulated glazing and hurricane-resistant frames, assembled off-site and installed using tower cranes and specialized rigging teams. Balconies, a hallmark of Miami residential design, were cantilevered with post-tensioned slab extensions, requiring careful engineering to mitigate deflection and ensure long-term durability in the saline air environment. Finally, staging and logistics played a pivotal role throughout the multi-year construction schedule. With multiple general contractors operating simultaneously on adjacent parcels, vertical and horizontal movement of materials had to be tightly choreographed. Dedicated staging zones, off-site prefabrication yards, and synchronized crane operations minimized congestion and ensured safety across the development. Beneath the waters and roadways of Miami, the PortMiami deep dredge and tunnel projects reshaped both the marine and terrestrial access to one of the busiest cargo and cruise ports in the United States. These two interconnected megaprojects required cutting-edge marine engineering, precision tunneling beneath a densely populated urban core, and rigorous coordination between federal, state, and local agencies to expand the port's capacity and streamline its logistics network. The Deep Dredge project aimed to deepen the port's main shipping channel from 42 feet to 50 feet, allowing for the accommodation of new Panamax-class vessels transiting through the expanded Panama Canal. To execute this, specialized dredging vessels were brought in, including cutter suction dredgers and trailing suction hopper dredgers, capable of removing millions of cubic yards of seabed material. The challenge lay not only in excavating to such depths, but doing so without disrupting sensitive marine habitats, port operations, or submerged utilities. Dredging operations were sequenced in phases, beginning with hydrographic surveys to precisely map the underwater topography. Blasting was employed in sections of dense limestone, with marine-safe explosives timed to avoid impact to sea life. The excavated material was carefully monitored and disposed of at authorized ocean disposal sites or used in beneficial reuse programs like beach renourishment. Environmental control measures included turbidity curtains and marine species observers aboard all vessels. Simultaneously, the PortMiami Tunnel project unfolded beneath Biscayne Bay. This initiative involved the construction of twin tubes running approximately 4,000 feet in length, connecting the MacArthur Causeway on Watson Island to Dodge Island, the heart of the port. The tunnels were designed to divert truck traffic from downtown Miami, enhancing safety and easing congestion. To construct these tunnels, a custom-built tunnel boring machine, nicknamed Harriet, was deployed. Weighing over 2,000 tons and spanning nearly 40 feet in diameter, the TBM was assembled in a launch pit on Watson Island and advance through a limestone substrate beneath the bay. The tunneling process involved simultaneous excavation and installation of precast concrete segment rings, forming the tunnel lining. These segments were waterproofed and grouted in place, forming a watertight shell that could withstand hydrostatic pressures and resist intrusion from saline water. Tunneling beneath the bay demanded constant monitoring of groundwater pressure, cut-ahead torque, and soil composition. The TBM operated with an earth pressure balance system to stabilize the tunnel face and prevent collapse. The spoil removed from the tunnel was conveyed by belt system to the launch shaft and trucked off-site. Crews worked in rotating shifts, operating around the clock to maintain excavation rates and minimize disruption to the bay and surrounding infrastructure. Once the structural shell was completed, interior systems were installed, including ventilation fans, LED lighting, fire suppression systems, CCTV surveillance, and emergency egress walkways. A robust stormwater drainage system was also built into the tunnel floor to channel any water intrusion into sump pits and eject it via high-capacity pumps. Taken together, the PortMiami deep dredge and tunnel projects not only increased the capacity and efficiency of port operations, but demonstrated how complex marine and tunneling engineering solutions can be successfully executed in a high-stakes, environmentally sensitive, and logistically intense urban setting. Towering above the Brickell skyline, the Panorama Tower in Miami represents one of the most ambitious high-rise construction efforts in Florida's history. With a height exceeding 800 feet, it stands as a benchmark in vertical development, blending residential, hospitality, office, and retail components into a single superstructure. Building such a skyscraper in a hurricane-prone, seismically inactive, but geotechnically complex coastal environment posed numerous engineering challenges that demanded both innovation and precision. Foundation work commenced with a comprehensive geotechnical survey to determine the capacity of the subsurface limestone bedrock typical of South Florida. The soil profile revealed layers of sand, silt, and coral rock, necessitating a deep foundation system capable of supporting the massive vertical and lateral loads. Engineers opted for a foundation composed of large diameter drilled shafts, some extending over 70 feet deep, socketed securely into the bedrock to prevent differential settlement. These shafts were reinforced with heavy steel rebar cages and filled with high-strength concrete, then capped with a massive mat foundation that was poured continuously over several days to ensure structural uniformity. The superstructure utilized a reinforced concrete frame system, chosen for its mass and resilience against wind loads, which are a critical design consideration for any structure of this height in a hurricane zone. The core of the tower, housing elevators, stairwells, and mechanical risers, was constructed using a slip-form system that allowed for continuous vertical progress. Surrounding the core, post-tension concrete slabs were used for the floor systems, providing high load capacity with reduced slab thickness, which helped to maximize ceiling heights within the constrained floor-to-floor space. Lateral stability of the tower was achieved through a combination of shear walls integrated into the core and strategically placed outriggers that tied the core to the perimeter columns at mechanical transfer levels. This configuration enhanced the tower's ability to resist overturning moments and sway, especially under hurricane-force winds. To monitor performance, embedded sensors were placed throughout the structure to track stress, strain, and movement in real time, feeding data into a centralized building management system. The tower's exterior envelope was composed of a curtain wall system featuring high-performance, hurricane-resistant glazing units with low-E coatings for energy efficiency. Each panel was factory assembled and tested for water infiltration, air leakage, and impact resistance before being hoisted into place. The facade was further reinforced at the corners and upper levels to account for increased wind pressures at higher altitudes. Mechanical, electrical, and plumbing systems were distributed across multiple levels with dedicated mechanical floors housing chillers, air handlers, backup generators, and electrical switchgear. These systems were installed with redundancy and flood protection in mind, given the potential for storm surge in the area. Chilled water loops and variable air volume systems ensured consistent climate control across the building's diverse spaces, from high-end residences to commercial offices. Vertical transportation was managed using high-speed elevators equipped with destination dispatch and regenerative drives to recapture energy during descent. Fire and life safety systems included pressurized stairwells, smoke evacuation systems, and multiple zones of sprinkler coverage to meet stringent code requirements for high-rise occupancy. Anchored along the banks of the St. Johns River in downtown Jacksonville, the development of Riverfront Plaza required a deliberate fusion of civil engineering, landscape architecture, and waterfront resiliency planning. The site, once occupied by the old Jacksonville Landing Marketplace, was reimagined as a dynamic public space integrating structural components with flood mitigation strategies, all while maintaining connectivity to adjacent urban infrastructure. From a construction and engineering standpoint, this project represented a complex interplay between environmental restoration, soil stabilization, urban utility integration, and open space programming. The first stage of construction focused on complete site clearing and demolition of the former structures. This phase involved selective dismantling techniques to minimize dust and vibrations, as the site is located near active traffic corridors, office buildings, and riverwalk segments. Demolition debris was sorted and recycled as part of a broader sustainability mandate, and existing below-grade utilities were mapped, capped, or rerouted to prepare the site for redevelopment. With demolition complete, the site was surveyed in high resolution to inform the grading and drainage plans. Given its proximity to the river and its susceptibility to tidal fluctuations and storm surges, the grading plan called for subtle terracing and the integration of bioswales to manage stormwater naturally. Fill material was imported and compacted in lifts, each tested for density and moisture content to prevent future settlement. Geotextile membranes were installed between fill layers to enhance soil stability and prevent erosion along the river's edge. One of the central challenges of the Riverfront Plaza redevelopment was the construction of structural retaining elements and hardscape features capable of withstanding both pedestrian use and hydrodynamic forces. Reinforced concrete retaining walls were formed along the riverwalk edge, designed with weep holes and subdrain systems to relieve hydrostatic pressure. These walls were anchored into the subgrade with helical piles in areas with softer soils, ensuring long-term stability against the variable forces of tidal surge and river currents. The plaza itself was constructed using a combination of cast-in-place and precast concrete paving systems, arranged in geometric patterns and supported by a subbase of compacted aggregate and fine leveling sand. Embedded conduits and utility chasers were integrated beneath the hardscape to support lighting, irrigation, and security systems. Special attention was given to expansion joints and surface drainage in the plaza design, with trench drains and permeable surfaces used to quickly shed water and avoid pooling during heavy rains. To support programming flexibility, the site included several utility stub-outs and foundational footings for potential future vertical structures such as pavilions or public art installations. Electrical cabinets and water connections were recessed and weatherproofed, and fiber optic conduits were installed for surveillance and wireless communication infrastructure. Landscape elements, including native trees, shrubs, and grasses, were selected for salt tolerance and deep root structures to minimize wind throw during storms. Tree pits were designed with structural soils and root barriers to protect adjacent pavement. Lighting was provided through architectural grade LED fixtures mounted on concrete bases, or embedded in pathways for both aesthetic and functional illumination. Stretching through the heart of Central Florida, the I-4 Ultimate project in Orlando represented a massive reconstruction and modernization of one of the state's most heavily traveled interstate corridors. The scale of this infrastructure initiative, spanning 21 miles, required an extraordinary application of highway engineering, traffic management, and structural design, all executed under live traffic conditions. The goal was not merely to widen the interstate, but to reconfigure it entirely to improve traffic flow, safety, and long-term capacity, incorporating express toll lanes, new interchanges, and updated overpasses. The initial phase of work focused on utility relocation and right-of-way clearing, including the removal of outdated bridges, underpasses, and surface roads. Utility coordination was especially complex given the corridor's urban setting. High-voltage transmission lines, water mains, gas pipelines, and fiber optic conduits were identified, surveyed, and in many cases rerouted through newly constructed utility corridors. Horizontal directional drilling and jack and bore methods were used extensively to install new conduits beneath active roadways without disrupting surface traffic. One of the hallmark features of the project was the addition of 4 managed express lanes in the center of the existing interstate. To construct these, engineers had to widen the footprint of the corridor and build new median support structures while maintaining the existing traffic lanes. This required extensive temporary shoring, phased traffic shifts, and the use of movable barrier systems. The new lanes were constructed with concrete pavement sections over a stabilized subbase and geotextile reinforced subgrade to support long-term heavy vehicle use. Bridges were a major component of the reconstruction effort, with over 100 new or rebuilt bridges included in the project scope. These ranged from short-span box girder structures to complex multi-level flyover ramps. Precast concrete beams were fabricated off-site and delivered during off-peak hours to minimize traffic disruption. Each bridge's foundation system was engineered to match local soil conditions, typically involving driven steel H-piles or drilled shafts. Bearing pads, expansion joints, and shear connectors were meticulously installed to ensure long-term durability and thermal movement capacity. The project's interchanges were completely redesigned to eliminate weaving and improve vehicular throughput. One of the most complex interchanges was the one at State Road 408, which required stacking multiple levels of traffic lanes, supported by tall piers and connected through sweeping curved ramps. Special seismic joints and post-tensioning systems were used in some of these long-span ramps to meet structural integrity standards and allow for maintenance access. Intelligent transportation systems were integrated throughout the corridor, including overhead gantries with dynamic message signs, cameras, and electronic toll collection systems. The express lanes were outfitted with barrier separation and entry-exit gates, spaced strategically to manage congestion. All ITS components were wired into a centralized traffic operations center, allowing for real-time monitoring and incident response.